Hello everyone, I'm Jungwon Park from Formulation University. Today, I will talk about online trajectory planning for multiple quadrotors in dynamic environments using relative safe-flight corridor. Let me start my presentation. The contents are as follows. First, I will introduce my research motivation, then I'm going to talk about the proposed method. Finally, I will show you our experimental results. Recently, multi-agent systems are receiving much attention due to various applications. To extend their achievable mission in dynamic environments, we need an online trajectory planning algorithm. However, there are two major challenges to achieve safe navigation in dynamic environments. First, we need future trajectories of obstacles to avoid them efficiently. But as shown in the right video, it is difficult to estimate their exact trajectories without prior knowledge. Second, as the number of agents and obstacles increases, it becomes harder to generate safe trajectory in real time. There have been many researches about online multi-agent path planning. However, many of them assume that all agents are cooperative to achieve their mission, so it is difficult to apply them in a dynamic environment. Some work such as VO-based method can deal with dynamic obstacles, but they require constant velocity assumption or communication to predict the obstacle's trajectory. In this presentation, we propose a new multi-agent trajectory planning algorithm for dynamic environments. This approach is based on relative safe-flight corridor, which can linearize the collision constraints continuously. By using this RSFC, we don't need to use a nonlinear solver for trajectory optimization. So as you can see in this table, our algorithm can generate safe trajectories for many agents in real time. For collision avoidance in dynamic environments, we need to consider the motion uncertainty of obstacles. Since the motion uncertainty increases over time, we construct RSFC to avoid their reachable region for each time segment. Therefore, our algorithm does not require constant velocity assumption or communication like other methods. Furthermore, we introduce a heuristic method based on reciprocal collision avoidance, which can improve solution quality. In this section, we explain our problem formulation. We suppose that there are n agents and no dynamic obstacles. For the collision avoidance, we adopt an ellipsoid collision model as shown in the right figure. We assume that each agent can observe the current position and velocity of all objects. And we also assume that dynamical limit of obstacles is given as prior knowledge. Due to the differential flatness of the quadrotor dynamics, we can express its trajectory as a polynomial form. Using this fact, we represent the trajectory of the agent as an m-segment Bernstein polynomial. Therefore, our goal is to find control points that make the trajectory continuous, dynamically feasible, and collision-free. We design the objective function to minimize the error to goal and derivative of the trajectory. We consider continuity and dynamical limit constraints to generate a continuous, dynamically feasible trajectory. For the collision avoidance, we'll use relative safe-flight corridor or RSFC. In this section, we introduce how to construct relative safe-flight corridor. As we mentioned in the previous slide, it is difficult to estimate the exact trajectories of obstacles. Some works utilize constant velocity assumption to predict the trajectories, but if the obstacles do not follow the assumption, there always exists a prediction error. To solve this problem, we estimate the maximum reachable region through its dynamical limit. In this work, we compute the maximum reachable region using the current velocity and maximum acceleration of the object. Since the actual trajectory is always bounded in the reachable region, we can get a sufficient condition for collision avoidance regardless of the prediction error. As you can see in the right figure, we can formulate collision constraint using inflated collision model. However, it is difficult to linearize collision constraint because it is formulated using Minkowski sum of two convex sets. For this reason, we use augmented collision model that includes the reachable region. As shown in the right figure, augmented collision model has the same shape as the original one, but a different size. After that, we linearize the collision constraint using augmented collision model. This figure shows the process of linearization. First, we plan initial trajectory of the agent. In this work, we compare two initial trajectory planners, the grid method and the view-based method. Next, we execute an affine coordinate transformation to make the collision model a sphere. It is possible because the augmented collision model is an ellipsoid. After that, we linearize the collision constraint at the closest point to the origin. We call this linearized constraint relative safe-right corridor. Since we represent the trajectory as Bernstein polynomial, we can reformulate the constraint using the control points of the trajectories. These videos show the construction result of RSFC. You can observe that RSFC is utilized to avoid reachable regions that increase over time. Although the RSFC works well on a small number of objects, it becomes invisible as the number of objects increases. Also, it is too conservative for inter-agent collision avoidance because RSFC doesn't distinguish between agent and obstacle. To alleviate these problems, we relax the RSFC using two heuristic methods, slack variable and reciprocal collision avoidance or RCA. The below figures describe the RCA relaxation. While the original RSFC makes the agent avoid the collision model completely, the relaxed RSFC allows the agent to avoid only half of it. It assumes that the other agent will take care of another half. As a result, we can get wider RSFC than original one. Return to our optimization problem, we can reformulate this to quadratic programming problem. Our objective function can be represented into the quadratic cost. Convex constraint can be transformed to affine equality and inequality constraints. We can replace collision constraint with relaxed RSFC. Therefore, we can solve this problem by using a conventional convex solver. These videos show the simulation result in an obstacle-free space. Compared to the BBC-based method, the proposed method shows a higher success rate and less transition time. The proposed method has more flight distance due to the conservative RSFC. However, we can alleviate this by RCA relaxation method. The proposed method takes more computation time than BBC-based method due to the additional constraints for the slack variables. But it is still stable for online trajectory generation for a large number of agents. Next, we conducted a simulation with 4 rotating dynamic obstacles. We note that it is difficult to predict the trajectories of rotating obstacles using constant velocity assumption. The table at the right side shows the success rate when the obstacles are slower than the maximum velocity of the agents. We can observe that the proposed method shows perfect success rate when view-based initial trajectory is used. We also conducted the simulation when the obstacles are faster than the maximum velocity of the agents. As the velocity of obstacles increases, the success rate decreases due to the dynamical limit, but it still shows over 70% and 30% of success rate respectively. This result shows that the proposed method can prevent a future collision by estimating the maximum reachable region of obstacles. Finally, we conducted a flight test with 4 crazy fly quadrotors. We assigned quadrotors the mission to patrol the 2 waypoints. and we sequentially computed the trajectories of all agents in a single computer. We use optitrain motion capture system to obtain the position of the agents, and we estimate the velocity of each agent by using a linear Kalman filter. The flight test was conducted for 196 seconds, and the video shows the part of them. As you can see in the right histograms, there was no collision during the entire flight despite the random movement of the pedestrian. In conclusion, we presented the multi-agent trajectory planning algorithm that can generate collision-free trajectories in real time. The proposed algorithm is scalable to a large number of agents and obstacles, and we validate the robustness of our algorithm by intensive flight tests. Thank you for listening to my presentation.